Okay, so in this video, I will jump to the other proof methods that you have to learn about in this course, namely a proof by case, proof without loss of generality that relates to the proof by case, and the backward proof. So in the last part, we learned about direct proofs, proof by contraposition, by contradiction, trivial and vacuously true proofs, and constructive and non-constructive existence proofs. And we ended the discussion with a note on um, incorrect proofs, where we are driven by the um, conclusion that we want to reach, and we allow ourselves to make certain pitfalls without checking in depth the soundness of every step in the proof. In this section, we will investigate more on proof strategies to prove different forms of arguments or theorems. The proof by case, backward proof, and the proof by case without loss of generality, they can be used when you are going from a certain premise to a certain conclusion, whether the premise is P and you're heading to Q, or doing contrapositive, going from not Q to not P, or going from P and not Q and heading to false. Okay, so in whatever type of proofs, you can use the proof methods that we are going to talk about right now. So the proof by cases. Assume we want to prove a conditional statement of the form P implies Q, and in case P is a disjunction of n different cases as follows, it's either P1 or P2 or Pn, then in this case, the goal would be to prove this conditional, in fact, to prove that whether it's P1 or P2 or Pn, finally Q necessarily holds. And logically speaking, this is equivalent to showing that P1 implies a Q and P2 implies a Q and so on until Pn implies Q. Okay, so for example, if you want to show that every integer has a certain property P of n, okay, well, sometimes the property may differ from positive and negative integers and maybe null. So in this case, you may proceed with n strictly positive, n equal to 0, and n strictly less than 0. Okay, so maybe this actually influence the way you can proceed with the proof of your property P. Okay. So yeah, this is just a rough example on when the proof by case may be useful to you. So in other words, to show that the first statement is true, P implies Q, we should show that for every I, Pi implies Q is true. Okay, we show that the property Q holds when P1, let's say, so in case of P1, it means when the number is positive. For P2, where we are assuming that the number is equal to 0, and for the final case where it's considered to be negative. So this kind of proofs is called a proof by case. Sometimes we can do exhaustive proofs, okay, which in which we actually consider exhaustive set of possibilities. Um, so it's a special type of proof by cases where the number of cases is small. In this case, we prove the argument by trying exhausting actually all the possible cases one by one. Example, we want to show that n plus 1 to the power of 3 is greater than or equal to 3 to the power n, but only for the positive integers that are less than or equal to 4. Well, this is a piece of cake actually, because it's sufficient to practically consider n equal to 1, 2, 3, and 4 included, okay? And then to show that this property holds, okay? I didn't check if it also, maybe also this works for 0, yeah, but you are requested just to prove it for positive integers, I'm sorry, okay? So To prove this, we use proof by exhaustion and by examining all the cases when n is equal to 1, 2, 3, and 4, as I said, and then the conjuncture is true for all the possible cases, and hence it's true. Okay, the original conjuncture for those cases. Good. Um, but this is not what we often use. Okay, so because this form of theorems, okay, um, is relatively quite easy to prove, as you may have seen. Uh, when it comes to universal quantifiers over a large domains, typically infinite domains, and you need to consider an arbitrary value from the domain. Well, sometimes it happens that your domain can be cut into several different ranges, um, and then in these ranges actually you will have different method to proceed with. Okay, so usually the proof by cases is relative to those particular cases where the property can be proved in different ways each time. So for example, to show that n squared is greater than or equal to n whenever n is an integer. So um, a property that talks about the correlation between the inequality between n squared and n. Um, and we want to prove it for any integer. Okay, so this is a typical example where actually we have doubts when it comes to the value of n, whether it's negative or not. Okay, but quickly we realize that, yeah, even if it's negative or it's null, it does not really matter. Okay, maybe the smallest value of n squared is when it's null, and then even then it would be greater than or equal. Okay, so yeah, there are three possible cases: n equal to 0, n is greater than or equal to 1, or n is less than or equal to -1. And I think that you can prove your inequality for the three cases, and hence you can show that this is always true. Okay. So you will often see such examples where the underlying property cries the use of proof by cases. Another typical example is when you have absolute values. So for example, if you would like to show that the absolute value of x times y is equal to the absolute value of x times the absolute value of y. Well, I think that the best way here is to proceed by cases. Okay, so you have actually four different cases. The case where x and y are both positive or null. The case where both of them are negative. The case where x is positive and y is negative, or the case where x is negative and y is positive. Okay, well, maybe currently you are thinking that actually cases 3 and 4 actually they are quite the same. Okay, because the multiplication operator here and there is commutative, and when you consider the case where x is positive and y is negative, okay, it's the same case of when you consider that um, y is negative and x is positive. Okay, it works also the other way around. Okay, because once you prove it for any two integers where one of them is greater than or equal to 0 and the second one is less than 0, so without loss of generality, you can also assume that it's also true for the fourth case. Okay, so we are going to talk about the without loss of generality in a couple of slides. But let's think about this property first of all um, in these three cases, let's say. Okay, so if you think about it, actually, it happens that the property holds in the three cases actually. Okay, and you can easily do the proof by replacing the absolute value of x or y by x if x is positive and or equal to null, and minus x if x is negative. And then the proof can be done for all these cases. Okay, you can do the same for the absolute value of y. Okay, guys. So great. Um, and by the way, unless you cut your various different possible cases or domain values into these particular chunks, you won't be able to make any assumption about the value of the absolute value of x times y. Okay, so you need to think about the sign of this value. Okay, and this really depends on the sign of x and the sign of y. Okay, and this is why we have these possible cases. The same applies here when you have x alone and y alone. Okay, good. So once this is done, you can say that your proof is concluded. Another example in which we won't give you the theorem, but we want you to come up with the conjuncture first and then to prove it by case. So the conjuncture that we want you to formulate is about the rightmost digit of a perfect square. What does it mean, a perfect square? So it's about those numbers that are um, a perfect square of integers. For example, 1 squared is equal to 1, 2 squared is equal to 4, 3 squared is equal to 9, 16, 25, 36, etc., up to 100, and you can also continue from there on. Um, and you have actually to think about the possible value that you have in the rightmost digit. So you can pause the video and think about it. Okay, and then when you get back, you will notice that the first digit can either be 1, 4, 5, 6, or 9, or also 0. Okay, so 6, 9, 4, 1, and 0, they repeat again and again: 1, 4, 9, 6, 5. Okay, but for example, you won't see 3, you won't see 7, you won't see 8. Okay, so they do not appear in this sequence, and neither 2, by the way. Okay, um, interesting. Okay, so but can we prove this? Can we say that the first digit in the perfect squares of any number is one of these values? Well, actually, if you write your number, okay, in this form, so you pick up any number and you write it as 10a plus b, where a is and b are non-negative integers, okay? So no matter what that number is, you can write it in this way. If the number is less than 10, well, it means it's equal to 10 times 0 plus the value n itself. Okay, so for any n that is less than or equal to 9. Okay, for the values that are greater than 10, well, you can clearly say that it's equal to some value times 10 plus b. Okay, so it's quite um, obvious. So now when you think about n squared, no matter what that n is, you will find that it's equal to 100a squared plus 20ab plus b squared. Okay, just think about this. Um, and if you think about it furthermore, you see that the only term that influences the value that we have in the rightmost digit, it's b squared, because this one is 10 times 10a squared, so it's okay. It cannot. You will always have a 0 in the rightmost digit in it, or even two zeros, by the way. And this one too. Okay, so you can also say that it's a plus 2 times ab. Okay, so these whole two terms are multiplied by 10, so they won't influence the rightmost bit. The only term that influences the rightmost bit is b squared. In this case, actually, um, we have to look into b squared and to check if b squared it cannot yield to any of the values 2, 3, 7, and 8. And it is actually the case because when you write your number as 10a plus b, okay, well, b would be a digit that is between 0 and 9, okay? And in this case, okay, so no matter what the number is, you will always end up having b equal to those numbers, 0 up to 9, okay? And it's sufficient to show that b squared in these cases will end up having in the unit part of it, in the rightmost digit, either 0, 1, 4, 5, 6, or 9, okay? And this is already done in this listing here. So if you check the first digits, actually, um, the perfect squares of any digit between 0 and 9, you find out that the square will end up having one of these numbers only, and it won't continue con contain 2, 3, 7, nor 8. And this is why actually you can um, generalize this conjuncture and say that for every n, it will always be the case. Okay, what about the proof without loss of generality? Well, actually, as I said in the example of the absolute values, we explored two cases that were quite similar, okay? They were dual actually to each other, and they would represent the same, practically the same cases, okay? Because the operator is commutative, and the role that x and y are playing in the formula is symmetric. Actually, it's the same. So this is why we can actually prove one of them and say that without loss of generality, the other case would also hold if the first one holds. So in general, when the phrase without loss of generality is used in a proof, we assert that by proving one case of a theorem, um, one particular case, okay? No additional argument is required to prove other specified case or cases, okay? So for one particular case, it might be uh, um, sufficient that once proved, it is also considered as a proof for some other specified cases. Of course, incorrect use of this principle can lead to unfortunate errors. Okay, so this could be among the famous pitfalls and in writing proofs. Um, and the reason is that sometimes the assumptions are made that lead to, in fact, a loss in generality, which is not desired. Um, Let's consider another example actually to show that if x and y are integers and both x times y and x plus y are even, then both x and y are even. So if you think about it, um, we can actually show the contrapositive actually. So we suppose that x and y are not both even, um, and then which means that either x is odd or y is odd or both, okay? And we can show afterwards that x times y and it's that it's not the case that x and y and x plus y are even. So the negation of this one is x times y or x plus y, okay, is odd. Okay, so either x times y is odd or x minus y is odd. Okay. Um, so we have at the first sight we have three possible cases: either x is odd, or y is odd, or actually both. Okay. Um, so, but you see that without loss of generality, it's sufficient to consider that x is odd. Okay. And then to study the possible cases for y, whether it's odd or not, yani whether it's odd or even. And then no need to do the proof the other way around. Okay, it's not needed to show that when y is odd and x is odd or even, it matters. Okay, so we can show that um, um, once we prove this for the case where x is odd actually, but on condition that we consider the case where y is odd or y is even. Okay, it already concludes the proof because starting again with the case where y is odd and x is odd or even, it's not necessary actually. It's equivalent to what we have shown so far. Okay, so this is also another example where the without loss of generality, a trick would spares us um, um, additional work, not necessary work. Okay, but let's see if we can really do this. If we can go from this premise to this conclusion. Okay, to prove the contrapositive. So actually, when x is odd, x is equal to 2m plus 1 for a certain integer m. And then now we show that x times y will be odd, or x plus y is odd. Okay? We actually can consider two cases, the case where y is even and the case where y is odd. So in case one where y is even, y would be equal to 2 times n. A quick look at the value of x plus y shows that x plus y is necessarily odd, okay? And when you pick up y equal to 2n plus 1, which means that y is odd, then you can easily show that x times y actually is equal to a certain odd number, okay? And this concludes the proof. Okay, so this completes the proof by contraposition, because now we can reformulate it as when x times y and x plus y are both even, then necessarily x and y must be even. Okay. Great. That, like, actually note that our use of without loss of generality within the proof is justified because the proof when y is odd can be obtained by simply interchanging the rules of x and y in the proof. Okay. So again, if you would like to know why this is working, because we're just dealing with addition and multiplication, and these operators are commutative, and even during the entailment phases, all the entailment phases, the role of x and y were interchangeable. So this is mainly the reason for this justifiable use of the without loss of generality trick. The last type or approach for proof that we would like to talk about with you, it's also a utility approach, if you would like to call it, that can be used with direct proof, proof by contrapositive, or contradiction. Okay, so it's called the backward reasoning. Okay, so to prove a statement Q, usually we start with a statement P that we know is true, and then we try to show that P implies Q. Okay, this is what we usually do with direct proof. But sometimes in P we don't see an information that is rich enough to reach Q, okay? And maybe Q is wrapped in a certain way that shows no correlation with P, okay? So it's completely legal. It's completely okay. It's even recommended, as we did this in the inference rules application. We were always driven by the conclusion that we want to prove, and we did certain backward chaining on the conclusion that we want to reach until we see a certain match with the premises. So it's completely fine. It's completely legal to do this. Also, when it comes to the proof of mathematical properties. So the direct proof approach is called forward reasoning, and is the most common type of reasoning used to prove relatively simple statements. But unfortunately, it's often difficult to use to prove more complicated statements because it's not always obvious which P to choose to reach Q, or which part of the truth that you have in P. So in such cases, it might be helpful to use backward reasoning. Okay. I think you get the idea from the next slide example. Um, but actually, to know what we do usually, we start with Q, and we analyze it. Actually, we try to check what we need to know, or actually what we need to have as true. What does it cost actually to make Q true? And we check if we can reach backward P, okay, or we can have a part of this truth, this needed truth or needed facts and properties. If we have part of them in P, if it is the case, then we can use that part of the truth and then rechain forward the facts one after the other until we reach Q. Example: if we were asked to show that the arithmetic mean x plus y over 2 of any two positive real numbers is always greater than their geometric mean, the square root of x times y, then we may turn in cycles at first until we figure out that a backward reasoning is maybe one of the easiest ways to proceed. Okay, so again, let's start from the conclusion, from what we want to show. We want to show that x plus y over 2 is always greater than, sorry, so it's always greater than the square root of x times y. Okay, so let's start from this and let's check what does it cost to have this property true. If you do it backward a little bit, well, um, let's multiply these numbers because we have x and y positively numbers. So we can safely say that x plus y squared is greater than 4 times x times y. Okay, and this can be shown to be as follows. So x squared plus 2xy plus y squared greater than 4 times x times y. Okay, um, and which is actually can be seen as x squared minus 2xy plus y squared is strictly greater than 0, which can be written as x minus y squared is strictly greater than 0. And now you see something that you can really uh, jump to it from the premise that you have, from the only fact that you have about x and y, that um, namely that they are actually both positive real numbers. Okay, so given x and y to be real numbers, clearly x minus y squared is strictly positive, and from there you can jump to this conclusion. So maybe in the beginning we couldn't see the correlation. Okay, from the fact that x and y are positive, it would entail plenty of facts, but it's only that one that matters to show this conclusion. So doing the backward proof or the backward chaining proof is really interesting sometimes, and the most helpful approach to prove certain properties. Okay, so I think you have the details here, and then this concludes this part too. Okay, so we can have further discussions on this part in our live session on Thursday. Thank you, and see you on Thursday.